Hello everybody, my name is Andro-Vasko. I will be going through this presentation today. I'm going to introduce the co-authors of this paper. Wolfgang Bein was my PhD advisor. Benjamin Cisneros and Janelle DeMonte are both students at UNLV, and they kind of help with the simulations and all those graphs and tables in this paper. So I'll be going over online competitive schemes for pseudolinear power down systems. So in our discussion, we're going to first do introduction and what we've been doing prior to this paper. We're going to go over the power down problem, online algorithms, the continuous state problem, which is what we're going to be sort of focusing on, and then we'll have conclusions at the end. So prior work, we've done some prior papers on power down problems using few number of states. We've also done with n states. There's been work done in that area as well. But we've mostly been focusing on sort of a power down problem with few number of states, which is actually more practical in some sense. We've done some work in taper down approaches, which is basically when a machine is on for a while, we can sort of power down a little sooner than we expected to save energy in the worst case. We've done continuous state stuff prior to this work, but on a different type of nonlinear based system. So anyway, for the power down problem, it's basically just a machine with a set of states. We can have n states, we can have a lot of states. It could be few, could be a lot, it could be continuous. And the idea is every single state has a standby or a cost to remain in that state, and also has a cost to power up. And typically, state 0 will be our sort of off, and then it doesn't really matter how we do this really, but we'll have one state off, one state on, have a bunch of intermediate states in between. They could be maybe it could be like a hibernation mode or sleep or screensaver mode, something like that. And as we go through on states to off, basically the idea is that every lower power state has a smaller amount of energy used to be in standby, and every lower power state has more cost to power up. So the on state has the most energy that's being used to be sort of in that state, but it has no power up cost. As we go to lower power states, each standby cost gets smaller and smaller, but the power up cost gets larger and larger. So think of it like a computer that's in standby mode uses less power than the on mode, but the standby mode has to power up in order to handle a request. And standby mode takes more energy to power up than already non-state, but if the machine is completely off, it takes the most energy to power to the on state. So the power down problem, we have several states, and we have requests that come in, and the machine has to be on in order to handle the request, and then we have to sort of find a way to schedule the system to minimize power consumption. So applications could be copy machines. So these machines here is a shared resource that people use, and it might actually it could take power to power up, and we've already handled this before. We've seen this happen if you've used a copy machine in the past. What will happen is you turn it off, it takes forever to turn back on. So having different sort of nifty tricks to efficiently schedule itself can be nice. Thermostats, so in some areas, which I've been to Japan once, or actually twice, and in Japan what happened was when you leave the room, the thermostat sort of activates some type of a timer, and it will turn off the AC after a certain point to save energy. Server farms, obviously a place where you want to sort of be careful. You want to efficiently schedule the machines. You don't want to have wasting too much energy there, so you want to make sure you are very careful about when you sort of power down the servers if there's not much usage for and no requests come in. And of course for the smart grid, they're small scale power plants, same idea. We use them when the nuclear power plant, the major plant, is not really being used too much. These smaller scale plants are kind of used there. So basically when we're powering down big nuclear power plant, then we're using this smart grid. So a couple of big, mostly they're large scale machines, kind of take advantage of this sort of power down problem. And this power down problem is going to be done in an online setting. So online algorithms are algorithms where the input is not known ahead of time. So we have to determine what's sort of the upper bound for the algorithm. So we first have to know what the offline cost is. So offline cost is produced by the offline algorithm. Offline algorithm is basically a case where input's already known ahead of time. You can easily compute the optimal cost. The online algorithm does not know what doesn't have the entire input given immediately. It sort of gets little inputs sort of step by step, and then it gets inputs one at a time essentially. It has to make decisions without any future knowledge, without any assumptions at all. You have to make a decision to try to minimize your cost. And the adversary for online algorithms is always there. Adversary is sort of, this person that tries to always find a way to make your algorithm perform as worse as possible. And we try to basically devise a schedule always that even the worst possible case, even against the adversary, we try to find a sort of a minimal upper bound is our goal. Oops. And then a competitive ratio is basically a ratio to online cost and the offline cost. So the input for the power down problem will be a set of requests, set of jobs. Each job has a start time and an end time, and you have a job duration. Now, for the power down problem, we don't really care about the job duration because we mostly focus on that idle time. So we can collapse the jobs like this. So all we care about really is during the idle time. So between time 1 and time 2, this idle time right here, we care about that essentially. We want to know how long that duration is, and during that time you have to sort of make decisions of, okay, when do we power down? If we power down too soon or too late, we can actually waste energy and have a bad sort of upper bound. So you want to find a schedule that will sort of minimize this. So this time between jobs is what we care about with this power down problem. So this theorem here, which was basically tells us that in the worst case, the competitive ratio was going to happen at transition time. So the idea here really is, let's say a copy machine, for example, you want to use that. Let's say somebody turns it off, and right when you turn it off, somebody wants to use that copy machine. Well, that's kind of the worst case scenario. So basically for this power down problem, the worst case scenario is right when you transition to lower power state, that's when the input comes in, and we have to power up, because remember, for the power down problem, it must be in on state in order to handle the request. If it's not in on state, it must power up first. So if it's switched to a lower power state and then a request comes, then really it could have been on for like a second longer. So that's kind of what this theorem tells us. So we're going to go into this continuous state machine. So the previous slides we had several states, each one has its own cost. Same idea here. So we have A and D. So A is going to be our unit cost or idle time, so the cost to be in state R, and D of R is going to tell us the power up cost. So we have infinite set of states between 0 to 1. So R is going to be between 0 and 1, where 0 is going to be the on state, and 1 is going to be the off state in this particular case over here. And we pick a state R, whatever R is, we can compute what its idle time will be, idle cost will be, and its power up cost based on these curves over here. So it's a linear sort of system. So as the R's transition towards 1, then the the idle cost will sort of decrease at this linear rate. And same thing as the increase, as we sort of go to lower power states, we're going to increase our power up costs by this sort of linear sort of curve by R essentially here. So we have these two other theorems over here. So basically we're sort of first we want to determine what's the efficient sort of offline cost. So we have in our paper, we have a proof for this, but we don't have time to cover this right here during this presentation. But the idea is, if the request comes between, let's say, so basically we're using this idle time of 1 unit. Now 1 is not really significant at all over here. We're just using 1 because we have all of our sort of curves normalized to 1, but we have some threshold value. We'll use 1 in this case right here. So if the request comes less than 1 unit of time, then the offline algorithm will just stay in the on state and sort of wait in on state until the request arrives. If the request comes after time 1, then it will sort of immediately power off and then just power up when the request arrives, because the offline algorithm knows exactly when the request will come, so it can easily determine whether to stay on until the request arrives or to power off immediately and then power up once the request comes. So if the request comes after 1 unit of time, it'll power off immediately, and since it's offline sort of case here, it knows when the request will arrive, so it easily can schedule itself like that. And then we're going to apply a few different strategies over here for this online algorithm. So we're going to first do this this logarithmic sort of curve we're going to apply to determine and pick states essentially in our in this case over here. So we're going to use this logarithmic strategy to determine what state to be in after R unit of time. So C in this case is going to just be some control parameter. R will be our wait time, and X of M is just basically our threshold. So in this case, it's going to be 1. And we can compute the cost by taking the integral of that curve and then apply the power-up cost at the very end. So let's go ahead and look at a few different different strategies over here. So we have these strategies here pictured. We have a bunch of C values. It just kind of tells us how the machine will switch from a high state to a low power state. So basically here, when we have sort of a very big C value, which is going to be this big number over here, this cyan curve is going to sort of model this strategy, which means that this strategy will power down from a high to low power state very quickly at the beginning, and at the end it will slowly transition down to the off state. All these have the same pattern, but for a small r value, so for example when it's 50, this red curve over here is sort of transitioning to lower power state at a slower rate than what's in cyan. So we have several C values, and those C values sort of determine the behavior as to how fast they're going to switch to lower power states. And using our sort of cost curves and our offline cost, we can compute our competitive ratios. So you see over here, the competitive ratios are actually pretty high, extremely high, to the point where it's not really the best idea to apply this algorithm, but we definitely worked on this and we saw which sort of strategies work best. Over here we see that, well, for the cyan color, the competitive ratio spikes to a very large level, then they sort of taper to a lower level, so the competitive ratios get smaller over time. And I sort of don't have the entire spectrum, so I could have had it go further, but I want to have this table look nice, or this picture look nice. But essentially, as the idle times increase, the competitive ratios decrease over time. They converge to the same, but they have this really bad case over here. So basically, this curve tells us the competitive ratio at various times. So if the request comes at several different times, the request happens over here at this time, competitive ratio for this particular strategy will be at this level. And if a request comes at a different time, this is going to sort of map or show the different possible competitive ratios for this algorithm. But essentially, the max of each strategy is going to tell us the competitive ratio for that particular strategy. So here's the table of various ones. So we can see here that the best competitive ratio is when the C value is arbitrarily smaller. But obviously, none of these are really too good, because the competitive ratio that goes these kind of high levels is sort of not a very practical sort of upper bound for online algorithms. So this is actually kind of an inferior case for this. So we're going to now look at this exponential strategy, which this is going to map the states in a different type of pattern using e to the value, so e to the x essentially. So once again, C again is going to be the control value, R will be our delay, our sort of our idle time between requests, and x of m is going to just be sort of our threshold when the machine will power down. And once again, same idea. We apply a strategy, we map it to a state, we get the cost of that state, and we sort of add them all up using this integral over here. So we integrate all of the costs of the strategy from 0 to whenever the request arrives, and then plus that power-up cost. So in this strategy for exponential states over here, we see this type of curve. So we can see if the C value is small, then we have this curve where it starts off kind of at a slow rate, and then it sort of transitions to a lower power state quick towards the end. Now cyan sort of curve here, when C is 6, then the system is sort of staying in the on state almost for a little while, and then it starts at the end very quickly transition to a lower power state. So if C is larger, it starts off during the idle duration, it'll stay in the on state or in a high power state, and at the end it'll just quickly switch to the off state. Now as a red, it has the same kind of pattern, but it's a bit more less extreme. It's going to start off in on state and it's switching at a slow rate between states, and at the very end it'll sort of go a little faster, but it's kind of relatively moving at the same rate throughout. But with a higher value, it starts off in high power state for a long time, and then it starts to just increase very quickly to a lower power state, eventually to the off state. And we see a competitive ratio in this particular case right here. We see that the one in red, so for a small e value, has the best competitive ratio, because all of these guys here have a low competitive ratio than the red one, but they all increase at the very end, towards the end of the idle duration before the machine would turn off. That's when they all get larger in the red than this smaller C value sort of strategy. So in this case over here, it appears that all of these strategies all are much better than the logarithmic strategy, but keep in mind that the red one, where the when the c-value is 2, it has the best competitive ratio overall, but only at the very end. So basically, even though at the end it's better, looks like in this case here it's better to use the other strategy, the larger sort of c-values, because for the most of the idle duration, it's going to be a better competitive ratio than whatever is in red over here. But the overall competitive ratio is better with the red, so it depends on how, if a system is very busy or very not so busy. But we have this sort of spectrums. Overall, the red one's the best one, but throughout the duration of the idle period, the other sort of strategies do perform better, except at the very end. So just kind of keep that in mind over here. So we have some more sort of examples worked out, more simulations we've done. So this gives us sort of all the competitive ratios, different c values. So we see right here that when c is smaller, it's going to give us better sort of results. And in general, the exponential sort of strategies perform a lot better than the logarithmic strategies for any various different cases. So let's go ahead and go to a conclusion. So in conclusion, we just sort of worked on this sort of this linear sort of system, and we noticed we tried using the exponential and logarithmic strategies on this system. It looks like, on average, the exponential strategy was much better, and a smaller c-value gave an overall better competitive ratio, but the larger c-values were performed better if idle duration was small between requests. And we want to take this problem and maybe apply different systems as well to see which systems perform better under what type of strategies, and also work out other strategies as well. So we did logarithmic and we did exponential. We can try other types of curves to sort of determine and pick our sort of strategies or states for online algorithm. And of course, we've worked on taper down algorithms in the past, and we want to be able to maybe apply these taper down where we power down at an earlier time in XM, depending on if the system is very busy or slack. So that's the end of this talk. Thank you for listening and have a great day.